Hello and welcome back to Calculus 1, section 2.7 on precise definition of the limit. This is something that was done in about 1850. So derivatives and integrals, the whole calculus technically emerged before the limits. And the limits are the thing that we use today to explain derivatives. And so it's interesting that we are going to learn this at the end of the chapter. That's the first thing. The second thing is that we are going to use all of that to define later on derivatives and some stuff for integrals. So what we have in this section is this what we call precise definition of the limit. So I gave you the street version, right? Limit is a fancy way to compute y value. That was the street definition. Now we're going to work on the definition of the limit, which is there, was created by mathematician Weierstrass, 1850, I believe, and that would be the definition. So here it is. So assume that function f of x exists for all x in some open interval containing point A, except possibly at A, so this is the beginning. Technically what it says, you have some function that exists for all x values in some open interval containing point A, except possibly at A. So the value A, that's the A that you're approaching, doesn't have to exist, right? Just to understand this right off the bat, you remember when you had this situation and you approach from the left, you approach from the right, and the limit is still here even though the point is not, right? That's the difference between pre-calculus and limit. So that's why this except possibly at A. It's for the cases like this, because here limit exists from both sides, we're good to go. So there's no ambiguity on this part. But here, actually, this is what I'm going to do now. Open interval containing point A. So this part of the sentence here is this situation, and this part of the sentence here is that situation there. That's technically, so both situations are captured as as we are setting up this definition. So now we say limit x approaches A of f of x equals L. So this is the notation. You are familiar with this. You've seen this for 2 weeks now. And here is the core of the definition. If for any number epsilon larger than 0, epsilon is the Greek letter that is technically our e, lowercase e. There exists a number delta larger than 0, that's like our d, such that, and now we have f of x minus L is less than epsilon whenever 0 is less than x minus A is less than delta. So what you see here is the formal definition of the limit. Now, this particular definition seems that it has a lot of words and is a very technical, but once you draw the picture for this, all of this stuff is immediately going to make sense. What you have to know before we draw these pictures is that epsilon and delta are extremely small numbers. They are positive, but they are extremely small. What is the size of an atom? Well, let's start looking at my size first, right? I am about 2 meters tall, and that would be, if I'm about 2 meters, right? If you take a meter and it is, right, the base unit, so half of me is 1 meter, which is a unit. Now, take 1 meter and get 15 zeros to the left to create 10 to negative 15. That would be the size of an atom. Atto size, atto. You have centimeters, millimeters, all of these nanometers, picometers, right? All of these units, micrometers, right? All of the units that are before, they have 10 to the negative 3, 10 to the negative 6, 10 to the negative 9, 10 to the negative 12, and then atto size, 10 to negative 15. That's where the atoms live. We cannot see atoms ever, because the wavelength of visible light is in, very good, nanometers, and this is smaller than that. So you can't see it. It's impossible. There's no machine that you can enlarge, right, and see it. So we have to use physics and brain to figure out the way they work, and we have particle physics and all the other things to understand. So when I'm talking about extremely small, I'm not even talking about that small, because you can go as small as you want, because you can put not 15 zeros, you can put 1,000,000 zeros if you want, right? It's mathematics. So when I draw this picture, because I have to draw big, right, so you guys can see, any of the distances for epsilon and delta, you will start thinking they are not thick as a hair. And you say, oh, that's small. No. You are going to go to insane thickness, right? For epsilon and delta. Those are going to be extremely small numbers, and you can make them as small as you want. And we're going to go from there. So now let's take a look at pictures. So this is the definition of the limit that you are responsible for. The question on the exam might say, state the definition of the limit. That's the definition of the limit. Pictures associated with this. Picture number 1 is going to be the existence of limit. And obviously, picture number 2 will be non-existence of the limit. So here I am going to have some function, f of x. I'm going to pick a value for a, which will return the limit L, because we know that the limit produces this. So now we see that a is associated with delta. So delta is on the x-axis, the width, and epsilon works with the y-axis. So what I'm going to do is I'm going to create a tube which is delta in width. And this is the delta that needs to be small, really small. And when you think you have it right small, make it smaller. That would reflect whenever it hits the function to the y-axis to create these epsilon right there. And now I can put in the measurements. This point over here is a plus delta, And this measurement here is A minus delta. You also have L minus epsilon and L plus epsilon as values. And if you are observing this as a tube that it's wrapping around the function, the lines, the black lines, right? I hope you can, in your mind's eye, as you squeeze here, the reflection is going to be squeezing around L. The more you squeeze here, the more it squeezes there. Squeeze, squeeze towards A, it's squeezing towards L. Remember, you're approaching from the left, and the numbers are going towards A, the numbers will be going towards L. You are approaching from the right, the numbers going towards A, the numbers will be going towards L. So both sides are going into L, so as you squeeze one, the other one squeezes, and then A points to L. Do we all see that on the graph? So if you want to squeeze here, right, for that part, squeeze here, you make the number smaller and smaller and smaller, so you make this epsilon smaller and smaller and smaller, then this one over here squeezes closer to A. So whether you squeeze here or there, they both together go, so A will point towards L at the end. So that's that squeeze. Do we all see that to some extent at least? One more picture and it's over. This next picture is one over x. And now, it's important to draw this nicely so you can actually see. I think it's good. Okay. So this is what I'm going to do. I'm going to pick, obviously, at 0, right? So that's my A. And then I'm going to put these deltas. Now, this delta has to go down, and this delta is going to go up. And then they bounce as a blue into the y-axis. So since these are deltas here, I have A plus delta and A minus delta as values here and here. Now, these blue ones are apart, but that's okay. They were apart before as well, right? So what happens now as I squeeze deltas? Do you see that as I squeeze deltas, the blue ones go even further apart? So when I bring delta in, like this, you see that the new blue ones are further apart than they used to be. So the first picture, as you squeeze on delta, epsilon squeeze onto L. But from the bottom picture, as you squeeze delta, those guys go apart from each other. And they do not meet. So, limit does not exist because these values, right, you cannot fit this separation that is trying to be infinite to be smaller than some finite small number on the y-axis. So, over here is limit does not exist. Nice one. So you can put a sentence if you want next to each one of these pictures. So the top one would be as you squeeze deltas on x, the y's would squeeze epsilons, right? Would squeeze. Contagious or something?
It's always true.
And that's it. That's 2.7. That's the precise definition of the limit, and the limit chapter is done and done. So,
Awesome. Time to go home?
no, we are going to take a short break. And first, like, subscribe, and what else? Notification, and what else? And smash the like button. Yes, you teach me all these things. Awesome. All right, bye.